Welcome everyone to my week 6 recap video. I decided to go ahead and make this tonight. The vast majority of you have already responded to the participation survey, so I think I have a good sense of what people are interested in seeing a little bit more review on. The vast majority seem to be interested in U-substitution and area between curves. So I have a few examples here. Of course, we only had a few sections, so there's fewer examples maybe than the last couple of weeks where we had the optimization and the curve sketching, right? Some relatively big topics. So we only have 3 examples, but I think that this should hit all the topics that people were interested in seeing. The other thing I do want to mention is because I'm making this video at home, I don't have all of my normal equipment, in particular my microphone, and therefore you're going to hear a little bit more tapping of my stylus because I'm just using the computer's microphone. But you know, I tried it out and I think it's definitely still going to be decent quality. So, okay, let's go ahead and get started with example number 1. So we're interested in finding the net area between the curve y equals x times the square root of x squared plus 3 and the x-axis on the interval from 1 to 3. So again, we need to remember that the net area, this is one of these keywords that was used for the definite integral, right? So the definite integral in this case, and the definite integral found this net area, right? Sometimes it was positive, it was above the x-axis, or if it was below the x-axis, we counted it negatively, right? So it's not true area, it's net area, right? Sometimes it's positive, but sometimes we count it negatively. So, okay, we're going to be integrating. The interval here is from 1 to 3, and we're integrating this function x times the square root of x squared plus 3 on this interval. So again, even though this problem does not say, hey, integrate this function, right, on this interval sort of deal, we need to remember that net area is one of those key phrases that means, right, that we want to integrate. So at this point, we need to decide, how do we actually integrate this thing? How do I find the antiderivative of my function? And the most powerful integration technique that we have is now thanks to 4.5, and that's going to be our U-substitution, right? So you can stare at this one and see if there's anything that you can do outside of U-substitution, but the claim is there really isn't. So we should try to, think about, can I apply U-substitution to this problem? And for about, I would say 80 to 90% of the problems, right, when you're trying to figure out what should your U be equal to, for around 80 to 90% of the problems, I would say that U is the inside function. So that's a good rule of thumb. It's not something that's 100% always true. And in fact, I have an example coming up of a case where that's not the situation. But as a good rule of thumb, letting U be the inside function is a good place to start. So in this case, my inside function, well, there seems to be this thing right here inside of a square root. So this kind of seems like, an inside function. So I'm going to go ahead and try U equals x squared plus 3. And if I do that, let's calculate out my differential. Du would be equal to, and when I take the derivative, I'm going to get 2x times dx. And we can now see that this is quite nice, right? We have a dx, we have an x, so we have all this stuff. So in fact, let me go ahead and rearrange this then, and I can make this du over 2 is equal to x dx. So I can trade in x dx for du over 2. Let's go ahead and do that. Du over 2. And we're going to have the square root of, and instead of x squared plus 3, I'm going to go ahead and write my u. I'm trying to get everything in terms of u's here. So now I have lots of u's, and we're going to go ahead and integrate this. Now when we're calculating out definite integrals, we can do one of 2 different methods. We can either switch these bounds, right? These are x values right here, right? From x equals 1 to x equals 3. We can either switch those to u values, or we can go ahead and just switch all of our u's back to x's at the very end and then plug in. So that's the way that I'm going to do. So I'm going to calculate out this indefinite integral. I'm going to go ahead and switch back, and then I'm going to plug in 1 for x and 3 for x. So let's go ahead and integrate this thing. So first of all, this division by 2, that's a constant. I can go ahead and pull that out of my integral. And then the square root of u, that's the same thing as u to the 1/2. So there's just a little bit of rewriting. Again, 1/2 is along for the ride. It's a nice constant. And when I find the antiderivative of this, remember I'm going to raise my power by 1. So I'm going to go from 1/2 to 3/2. And then I'm going to multiply by the reciprocal of my new power here. So this is going to be 2/3. And of course, this is supposed to be an antiderivative. So we can check, if you take the derivative of this, do you get back to where you started? Well, if you take the derivative, the 3/2 would come down, perfectly cancel out with a 2/3. I'd reduce my power by 1, so I'd go from 3/2 to 1/2. So yeah, this seems to be working out well. All right, so let's go ahead and do a little bit of cancellation here and just simplify this down. So we're going to have 1/3, and instead of u, let me go ahead and rewrite this as x squared plus 3. This is going to be raised to now the 3/2 power. And remember, I want to evaluate this from 1 to 3. So that's from x equals 1 to x equals 3. So if I go ahead and I plug in 3, let's see, I'm going to have 3 squared, that's 9, plus 3, that's going to be 12, raised to the 3/2. And then I'm going to subtract away when I plug in 1. So if I plug in 1, this is going to be 1 squared, that's 1, plus 3 is going to be 4, raised to the 3/2. So we can go ahead and leave our answer like this, or actually 4 raised to the 3/2 power can actually be simplified down. So we know that 4, well, when you raise something to the 3/2 power, that means you have to raise it to the 3rd power, and you also have to raise it to the 1/2 power, but the order's up to you. So I'm going to go ahead and raise it to the 1/2 power first, because I know raising to the 1/2 power is just the same thing as the square root. Oops. So it's going to be 2. And then remember, well, I raised it to the 1/2 power, but I also have to raise it to the 3rd power. Right? So if I raise 2 to the 3rd power, that's going to be 8. So my final answer here would be 8. So we're going to have 1/3 times 12 raised to the 3/2 power minus, and again, this was 8. So I'm going to do 8/3 here. And that's kind of as simplified down as I can possibly get it. So that right there would be my final answer. So again, I like this problem because it kind of combines together a couple of ideas. Back from 4.2, right, this net area under the curve, the definite integral, right, what is the definite integral used for? Well, net area under the curve. So that was 4.2 and 4.5, right? So we had to, in order to evaluate out this integral, we needed to use U-Substitution. Okay, I told you that in this case, right, our u should be the inside function, right, and that this was a good rule of thumb. But it's not 100% always the case, and so I wanted to show you a situation, an example number 2, where we find the average value of this function on the interval from 0 to pi over 2. And first of all, even before I get started with this, I want you to be careful. Oops. So maybe just be careful when you're reading these sorts of things. We have 2 topics in this class that are if you're going too quickly, they're very similar to one another, right? We have the average rate of change, of a function. And again, we're given an interval for this and all that. And this was kind of way back at the very beginning, right? 1.4. So chapter 1, section 4, we did the average rate of change kind of before we did the derivative, right? The derivative is instantaneous rate of change. We talked a little bit about the average rate of change. And now here near the very end of the course, right, we get this average value of a function. So average value of a function or average rate of change. Again, if you're going too quickly, right, you could interchange these and you would mess up kind of the entire problem, unfortunately. And again, this average value of a function was from 5.5, one of the topics that we brought up this week. All right, so we need to remember the formula for average value of a function. All right, I'm going to go ahead and write average value of f. This was equal to the integral from a to b of f of x dx, and we needed to multiply by this 1 over b minus a sort of deal. So since we have our interval from 0 to pi over 2, this is going to be our a value, and this is going to be our b value. So in our case, we're going to have 1 over pi over 2 minus 0, and we're going to integrate from 0 to pi over 2 of sine of x times cosine of x dx. And we go ahead and do one more line of simplification before we do the antiderivative. So 1 divided by pi over 2, well, minus 0, so that's just going to be 1 divided by pi over 2. Whenever you divide by a fraction, you could also multiply by the reciprocal. Right, so this is just going to simplify it a little bit here. So 2 divided by pi, and now I want to go ahead and take the antiderivative of this. Right, sine of x, cosine of x. And the claim is, right, maybe before this week we had no idea how to find the antiderivative of this, right? There's no product rule for antiderivatives. So we need to use something, and the claim is, well, again, the most powerful integration technique that we have is U-Substitution. So if you don't know how to integrate something, I would try U-Substitution, right? So, okay, in this case, let's go ahead and try U equals something. And in this case, right, I said the good rule of thumb would be U should be your inside function, but as I look here, there doesn't seem to be really any inside function. Right? There's sine and there's cosine, and both of them seem to be, as you know, they both seem to be outside functions. So the claim is, well, we just need to try something, right? And this is going to be something that, you know, again, this problem kind of breaks the rule of thumb a little bit. So we just need to try something. I'm going to go ahead and try, what if u was equal to sine of x? Well, let's go ahead and take the derivative. Du would be equal to cosine of x dx. And we can now see, that's very good, right? So we have a cosine of x dx. I can go ahead and absorb that in du. And we have, of course, one of our sine of x's. That's just going to be my u. So let's go ahead and trade all this in. So this is going to be, again, 2 over pi, the integral, and I'm going to go ahead, sine of x is u, and cosine of x dx is du. So I'm going to go ahead and integrate this. So when I integrate just u with respect to u, again, I need to raise my power by 1, and I need to multiply by the reciprocal of my new power. And this is 2 divided by pi out here. So, okay, the 2's will cancel out very nicely. And then let's go ahead and substitute back in for our x's. So this is going to be 1 divided by pi, and now u squared. Again, u was sine up here. So this is going to be sine squared of x, and I'm evaluating this from 0 to pi over 2. So if you plug in pi over 2 everywhere you see an x, this would be sine of pi over 2, that's 1 squared. So 1 squared, of course, is just 1. So this is going to be 1 over pi. Subtract away when I plug in 0. Well, sine of 0 is 0. Square that, still 0. So this is going to be 1 over pi minus 0. So my final answer is 1 over pi. So again, this is a nice problem because it's combining together a couple of ideas. We had to use U-substitution in order to solve this, and it was an average value of a function. So this kind of covers, again, 4.5 here, the U-substitution, along with average value of a function, which was 5.5. So as I read some of your comments about the participation survey, I definitely saw a lot about U-substitution, so I wanted to make sure that I hit that. The other comment that I heard was definitely some of this area between curves, and in particular, some of you mentioned very specifically when there were 3 curves involved. So I thought, okay, let's go ahead and do one of these that's not only an area between functions, but we're going to involve 3 curves with this and see how would we tackle such a problem. So let's remember the underlying concept here before we get started. If you want to find the area between some curves, maybe f of x and g of x or something like this, right, you're going to do the integral on some interval from a to b, and you're going to do your big function, maybe f of x, minus your smaller function, g of x. Oops. And this is going to be with respect to x. So that is if you have y is equal to f of x, and y is equal to g of x, right? This is maybe your setup here. So you have y equals. The other option is that if you have x equals some function, so maybe you have x equals h of y, or x equals, let's see, f, g, h, let's use j maybe, j of y. Then you could do the integral from maybe c to d, again integrating with respect to y, and now you do your big function, so maybe h of y, minus your smaller function, maybe that one's j of y. So you have a couple of different scenarios that you could set this up with. So when I first encounter this problem, I see that all of these functions, they're all solved y equals, y equals, y equals, y equals, right? And so this is leading me to believe that maybe this first way, right, where you have to have y equals some function with x's in it, y equals some function with x's in it, maybe this first way with integrating with respect to x will be better. It's hard to be certain, though, without a picture. So let's go ahead and sketch this and see exactly what's happening. So, okay, my first curve, I'll go ahead and use purple here. Y equals 1. That's a nice, easy one to draw. So it's just a nice horizontal line, and the height of that's 1. Y equals x is also not so bad. Y equals x. So this is a line with slope 1 that goes through the origin. And maybe we want to see where these things intercept. So if I go over x equals 1, I'm going to go up y equals 1. Right? So maybe something like this. Here's my curve y equals x. And then finally, maybe my most complicated curve, but still all things considered, it's not too bad. We have y equals 7 minus 2x. So this is a curve that starts up at height 7, right? So 1, oops, that's not spaced out correctly. 2, ooh, the computer's going a little bit crazy. There we go. 2, 3, 4, 5, 6, 7. I want to do my best to draw this to scale as best as possible, so sorry that I'm running into kind of my other stuff up here. In fact, let me go ahead, I'll try to cheat using the power of technology, which sometimes works, you know. Let me go ahead, try to take this and I'll move it down. That worked out all right. Okay. So it starts up at height 7. Again, that's if I was to go ahead and plug in 0 in for x, right? I'd have a y value of 7. And notice maybe if I was to plug in an x value of 3, so x equals 1, 2, 3. If I plugged in an x value of 3, we would have 7 minus 2 times 3, that would be 6. So 7 minus 6. So that would have a height of 1. So, okay, let me go ahead and try to draw my best straight line here. It's relatively okay. So we can see that these three curves together kind of entrap, right, this kind of triangular region here. So this nice triangular region, and this is the region that is bounded by these three curves. And our goal is to find the area of this region. And so now at this point, I start to realize that there's going to be a problem if we go ahead and integrate with respect to x. So if we integrate with respect to x, remember we need a big function minus a small function. And the problem here is that our big function seems to be changing, right? Because for a little while, it looks like this orange function is our big function, right? Y equals x seems to be our big function, and then y equals 1 is our small function. Right? When I say big, I mean that its y values are big. Again, we've solved y equals. So again, I'm talking about big y values. So it's kind of higher up. However, later on, right, on the next interval, maybe I'll use black here, right, this red function right here seems to be our big function. And again, kind of our small function, our smaller y values, are still given by y equals 1. So actually, I would need to go ahead and split this up here, and I would figure out the area here, where I have, you know, kind of one big function minus one small function, and then I would have to find the area here. One big function minus one small function. So this is maybe less than ideal because I would have to split up the integral and I'd have to calculate out two things, right? The claim is that actually if I do this with respect to y, instead, life works out a little bit nicer. Again, let me explain why really quick. So if I go ahead and maybe erase some of the stuff, or actually let me kind of back up here, so that way this stuff doesn't even show up. These black lines and these blue lines. All right. One more. There we go. Okay, so if I was to integrate with respect to y, notice that I have x equals things. So when I set this up again, I need my big function minus my small function. but now the big values and small values are x values, right? They're no longer y, but they're x equals things. So when I say big, I mean that it has big x values. So you can see that this red function over here has it's the big function. It has bigger x values, right? And the small function would be this one, y equals x. It has smaller x values. So actually, if I was to integrate this with respect to y, I would only have to calculate out one thing rather than two things, right? So I'm going to go ahead and integrate this with respect to y. But if you are insistent, right, you want to integrate this with respect to x, it's certainly possible, right? And that may be a fun thing to do, to go ahead and pause the video, integrate it with respect to x, and we should get the same answer, right? We're finding the same areas here. All right, so again, I said I was going to integrate with respect to y. So let's go ahead and set up our integral. Again, we're going to have our big function. That's going to be my purple one that I've highlighted down here in purple, minus my green function. Oops, I'm going to use this. Now I'll go ahead and write those in just 1 minute, integrating with respect to y. So again, this purple one right here, right, this is a part of, well, this bigger red function. That was 7. Oops, sorry, I need to kind of go up here. That was part of this y equals 7 minus 2x. But remember, I need x equals things. I need x is equal to a function and it can have y's in it. So I need to go ahead and take this and I need to solve it x equals. So let's go ahead and rearrange this. I can get 2x is equal to 7 minus y. And then I can go ahead and divide by 2. So that's going to give me x is equal to 7 minus y, all divided by 2. All right, so let me go ahead and write this down here. And in fact, I'll go ahead and distribute that division by 2. So I'm going to write 7 halves minus y halves. Or 7 divided by 2 minus y divided by 2. All right, so that is my big function. Now let's go ahead and subtract away my smaller function, right? So my smaller function was this green one right here. It was part of y equals x. So y equals x. Again, I need to solve this x equals, but it's easy to do, right? It's already solved x equals, so that's just going to be y. Again, when you're integrating with respect to y, we should have all y's here. There shouldn't be any x's. All right, finally, we need to know what are our y bounds of integration, right? Where do we start and when do we stop? Well, it looks clear to me that we're going to start at y equals 1. That's the smallest y value that's kind of a part of this region. And we need to stop here, right? This is kind of the biggest y value that's a part of the region. And I don't know, just by looking at this, it seems like it's maybe around height 2, maybe a little bit smaller. But in order to find this exactly what it is, right, I need to go ahead and use algebra, right? This seems to be where the red line crosses with the orange line. So the red line, again, was this 7 minus 2x, and the orange line was y equals x. So let's go ahead and set these equal to each other. I would have x is equal to 7 minus 2x. And so I'm going to get 3x is equal to 7. So that's going to give me x is equal to 7/3. All right, so that's the x value, but I need the y value. So I figured out what x value it's equal to. I need to figure out what y value. So, well, I can just take this and I can plug it in to either one of these functions. In particular, it's quite easy for me to plug it into the orange one here, this y equals x. So if I plug in 7/3, I'm going to get y equals 7/3. So this is saying that that height right there is y equals 7/3. And so again, you can say, this is a bit of a pain going through all of this work. But remember, if you wanted to integrate this with respect to x, you'd be doing about, double the pain, right? Because you'd have to, again, break it up into 2 regions, and you have to calculate out 2 antiderivatives and all this stuff. So the claim is we are actually saving ourselves some headache here. Let's go ahead and simplify 1 to 7/3. And this is going to be 7 halves. And let's see, I have negative y halves, and subtract away. Let me go ahead and multiply by 2 on top and bottom here, just so that we have a common denominator. And so when I subtract away, let's see, negative y divided by 2, subtract 2y divided by 2, that's going to be negative 3y divided by 2. Again, we're integrating with respect to y. So when I do that, well, if you integrate a constant, you're just going to have y here, so 7/2 times y. Again, if you take the derivative, you get back to where we started. And then here we're going to have maybe, what, 3/4 y squared. Again, double check. If you take the derivative of this, the 2 would come down, cancel a little bit with a 4. So yes, you'd get back to where you started. And now we need to go ahead and plug in from 1 to 7/3. So when I plug in 7/3, let's see, I would have 7/2 times 7/3 minus 3/4, and 7/3 squared, so that's going to be 49/9. So not very beautiful thing. When I plug in 1, let's see, I'm going to have 7/2 minus 3/4. So a little bit nicer here. Now, if I was on the exam or something, I wouldn't spend too much time simplifying, but one thing that I do notice, right, is there's the 3 here and the 9 here. That's going to cancel a little bit. So I would probably write this as what? 49/6 minus 49/12 and minus 7/2 minus 3/4. I would simplify it at least down to here. Again, I wouldn't spend too much time simplifying this if it shows up as a free response question. If it shows up as a multiple choice question, right, and you don't see an answer like this, well then of course you can keep on simplifying until your answer matches one of the things that you're given. If you went ahead and simplified it all the way, just as kind of an FYI, it does give out a relatively nice thing, just 4/3. So if you continue to simplify down, you do get a nice answer, 4/3. All right, and there is my third and final question. I'm amazed, only 3 questions, but I still managed to take over, 25 minutes to kind of go through these. But I hope that I've explained it in enough detail that kind of it makes sense, kind of why I'm taking the steps that I'm taking. Also, kind of as an FYI, I did also sketch this out on a Desmos app here. Let's see, there it is. So we got a picture that looks very similar to this. Again, if you were to integrate this with respect to x, you would need to break it up here. And you would need to find the area of this red triangle and the area of this blue triangle. However, integrating with respect to y, you're able to do this kind of in one fell swoop. That's because there's kind of one big function, x equals, right? One big x function and one small x function. But that's not the case, right? If you're integrating, y equals stuff, right? If you integrate with respect to x, with your y equals, right, there's not one big y function and one small y function. There's actually 2 different big y functions, here and then later on here. So that's why integrating with respect to x, it just takes a little bit longer. It's not impossible by any means, but it just takes a little bit longer. All right, so I hope that you've enjoyed this video. And yeah, good luck on the final exam tomorrow. Again, I wanted to make this here tonight just so I know that there's some people who are taking it rather early tomorrow at alternate locations and things like this. So I just wanted to make sure that everyone would have time to watch this and benefit from some of these more thorough explanations. All right, so again, good luck tomorrow, and I'll see you out there. Thanks.